Welcome in this video. In our previous video, we implemented the ADAM algorithm, and in this video, we are going to implement the Rectified ADAM algorithm, which corrects some of the flaws of the ADAM algorithm. These are the results we'll get by the end of this video. So this is the testing accuracy on the MNIST dataset as a function of the number of epochs, and we can see that the results of our implementation are very similar to the PyTorch implementation. So let's dive into the implementation. As usual, we'll use PyTorch on a few other libraries such as Seaborn on Matplotlib for putting the results, on Keras, but just for loading the MNIST data. So you don't have to download them manually on your computer. Okay, we can start by calling this function load data to load the training and testing MNIST data, and then we can directly dive into the ADAM implementation. So we take as input a model, so a PyTorch model, a learning rate alpha, on beta 1 and beta 2 for computing the running gradient average. So we can start by initializing a few variables such as the first order momentum, mt, the second order momentum, on storing the hyperparameters such as beta 1, beta 2, the learning rate, and epsilon. And now comes the big difference with respect to ADAM. There is this variable rho_inf that we'll use in a bit. So as with PyTorch, all optimizer have two functions, 0 grad and step. So the 0 grad function set back the gradients to 0. So we iterate over all the parameters in the model, and we set back the gradients to 0. Because otherwise, PyTorch will accumulate the gradients, which is useful when you want to do heavy computation, but your GPU memory is too low. So what you do, you accumulate the gradients, and only when they are when you have accumulated enough gradients, you can do a gradient step. But this is very important to do the 0 grad function. Otherwise, your gradient will accumulate and will never be instantiated back to 0. So now that we've done that, we can implement the step function that will take the gradients computed by the backward function and do the parameter update. So those 4 lines are very similar to the ADAM implementation. So we iterate over all the model in the parameters, in the model, and for each of them we compute the first order momentum and the second order momentum based on the previous values. So self, m and v that are stored in self.mt and self.vt, and we update them recursively. Then what we can do is compute this variable rho that is also, I think, no, it's not computed in ADAM, so we compute this variable, and then we check if this value is greater than 4. If yes, we do the gradient update with this formula. If no, we do another gradient update. This one is very similar. It's just similar to standard gradient descent, but we are using m instead of the gradient. And now we can dive into our training function. We take as input a model, an optimizer, a loss function. So we are doing classification on the MNIST dataset. So we'll use the negative log likelihood loss, and we have a number of epochs on the batch size. So we iterate over all the number of epochs required. On doing each epoch, we sample a batch of data. We compute the log probability predicted by the model, and we compute the negative log likelihood loss by comparing the predicted probabilities on the real classes in the variable y, which comes from the label of the training data. Then we can call our 0 grad function. We can backward the loss and do an optimizer.step. We made our implementation generic. That means that you can take as input our optimizer that we've just implemented, or any optimizer from PyTorch. And what we can do is every 100 epoch we can log the testing accuracy, so that we can see it. We can see the evolution over time and plot the graph that I've showed in the beginning of this video. Now we can dive into the main function and put all the pieces together. So we'll train on GPU if it's available, otherwise on CPU. But usually we just want to go to GPU. It's just too slow on CPU. We will compare our implementation with the PyTorch implementation. So I'm creating 2 labels for each of them. And then we iterate over both optimizers, either the optimizer from PyTorch or our optimizer. For each of the optimizer, we create a model, so a very simple MLP that predicts log probabilities. So we use the log softmax for the last activation function. Then we create our optimizer. The PyTorch optimizer is taking the parameters directly as input, so model.parameters, while in our implementation we take the model directly as input. So if it's PyTorch, we feed model.parameters. If it's our implementation, we feed the model. Maybe we could have adapted our implementation to take the model.parameters, so that our implementation would have been very similar to the one from PyTorch. That's very easy to do. We could do it. Then we launch the training function on our model with our optimizer. We get back the testing accuracy and we plot it for each of our optimizer. And then we can add a few more labels to the plot, such as the Y on X labels. We can add the legend and save the figure. I really hope this video was helpful to you to understand a bit more optimizers, the ADAM optimizer, which is very widely used. Now the RADAM optimizer starts to be more and more used, so maybe you should switch to from ADAM to RADAM. Of course, it depends on your problem, but that's great to understand how it works. I really hope it was helpful to you. If it was, please leave the thumbs up and subscribe for more videos like that.